Hello everyone and welcome to our series on systems of equations applications. Today we're going to be talking about the application often known as current problems. Current as in like the current in a stream. We could be talking about a stream of water though, a stream of air. Basically the idea is that we are traveling in one direction with a rate, but there is some sort of resistance, wind or water coming against us, which is slowing us down if we're going against the current, but it's speeding us up if we're going with the current. So that's going to basically lead to our equations here, kind of an upstream, downstream, or with the current, against the current equation. All right, so let's look at some examples and we'll see how that all plays out. It says a plane travels 1,200 miles with the wind in 2 hours. The return trip against the wind takes 3 hours. Find the rate of the plane in calm air and the rate of the wind. So basically we're trying to find the rate of the vehicle on its own, how much it's pushing itself, and then how much is the rate of the thing that's coming against us, the current coming in the opposite direction. So those are the things we're looking for, and as always those are going to be our variables. So let's go ahead and say x is the rate of the plane in calm air. So if there was no wind at all, how fast would the plane go? Y will be the rate of the wind. Now, one of the large concepts underlying this is the relationship between distance, rate, and time. So sometimes people will call it the dirt equation because distance is equal to rate times time, and it kind of looks like the word dirt. So we're going to create a little table that's going to hold all the information in this problem neatly. You don't have to, but this is a nice way to organize your thoughts. So our table here, I'm going to make kind of the first row of it is going to be kind of our upstream, and the second row here will be downstream. And we're going to basically set up each piece of this puzzle here. So I'm going to start with the rate, add in the time, and we know that if we take rate times time, we will get our distance. Great. So a plane travels 1,200 miles with the wind in 2 hours. The return trip takes 3 hours. But if it's a return trip, both upstream and downstream are going to be the same distance. Many of these problems have the there and back kind of aspect to them, so the distance both ways here is 1,200 miles. They also here tell us the time. They tell us the time that it took to go upstream, I'm actually rather downstream is going to be 2 hours. That's kind of going downstream with the current. And the return trip against it takes 3 hours. Great. So if x and y are the rates of each piece, the plane and the wind, why are they contributing to different amounts of time? Well, if you're going with the current, it takes less time because those two speeds kind of get added to each other. You know, hypothetically, if you were traveling 5 miles an hour and you were running on a belt that was going 2 miles an hour, those two speeds would add up together and you'd be going 7 miles per hour. So we're going to add those two together. So the rate down is x plus y. The reverse is also true. If you're running 5 miles an hour but you're running in the opposite direction of a belt, that 2 miles an hour is going to take away from your speed. So you're going to end up going 3 miles per hour. So your rate, we're going to take away the rate of the wind. So this kind of ends up being something you'll see all the time, is that when you're going against the current, you're subtracting from your speed that current's speed. And when you're going with the current, you're adding those two speeds together. So this leads us to two equations because we know that rate times time equals distance. So this leads us to, I'll write it just as it is. So x minus y, it's important to put those in parentheses, times 3, that's rate times time, is equal to distance. And similarly, x plus y times 2 is equal to 1,200 again. I'm just going to clean those two equations up by distributing our numbers outside here, our times. So 3x minus 3y equals 1,200. and 2x plus 2y equals 1200. And now I've got a system of equations that I can solve using all of our favorite tricks. So to me, that system looks like it's really set up for elimination. I'm going to go ahead, I'm going to multiply this equation by 2 and this equation by 3. I'll rewrite those up here. So the first equation is going to be 6x minus 6y is equal to 2400. And the second equation will be 6x plus 6y is equal to 3600. Great. So now we can go ahead and add those, and the x's will add together to get 12x. The y's will cancel out, and we'll get 6,000. So then we can go ahead and we can divide both sides by 12, and we get that x is equal to 500. So that is the rate of the plane in calm air. So let's go ahead and find out what the rate of the wind is. So we can go to any of our equations. We can go back to the original here. It might be safe to go ahead with one of the equations here. So 3 times 500 minus 3y equals 1200. So 1500 minus 3y equals 1200. So we subtract 1500 from both sides, 1500, and we get negative 3y equals negative 300, and we divide by negative 3, and we get that y is equal to 100. So the wind against, very heavy wind, is 100 miles per hour against us. So let's finish by just answering the question. The plane can travel 500 miles per hour in calm air, and the wind is traveling or gusting at 100 miles per hour. Great. We could plug both of those numbers into our problems and see that we would get 1200 for the distance. So basically 500 plus 100 would be 600 for our downstream times 2 equals 1200. You can quickly see that that's true. For our other, we get 500 minus 100 would be 400 times 3 equals 1200. And again, we can readily see that that's true. That kind of confirms to us that these are the speeds for the plane in calm air and the wind against us. Let's look at a second example. They're going to try to throw a little extra tricks at us, but nothing to fear. So a canoe covers a distance of 40 miles in 6 hours. Returning upstream, it takes the canoe 3 times as long to cover 3/5 of the distance. Okay, let's go ahead and set up our distance, rate, time little table here. Add one more row there. So we've got rate, time, and distance. And we've got downstream, and then we've got upstream. So they didn't really mention the first part is downstream, but they said returning upstream. So downstream, they told us the distance was 40 miles, and they told us the time was 6. Oh, what did I forget to do? Forgot to define our variable. So let's let x equal the rate of the canoe in still water, and y equal the rate of the current. So here we've clearly changed from air to water currents since we're in a canoe. So the rate downstream here is going to be both the x and the y added together because they are helping each other to go faster downstream. Now, here's the little trick. They said returning upstream, it takes the canoe 3 times as long. Well, we're not too tricked by that. If it took 6 hours before, now it's going to take 18 hours because that's times 3. But they also said that it's going to only cover 3/5 of the distance. So it was 40 miles, so I'm just going to say 3/5 of 40 for the time being, just so we can see where that works coming from. We'll calculate that in just a second. But of course, if we're going upstream, we're taking the speed of the canoe and we're subtracting the rate of the current because that's slowing us down. So this is going to lead us to our two equations. So x plus y times 6 is equal to 40, and x minus y times 18 is going to give us 3/5 of 40. Okay, let's clean both of these equations up a bit. The top equation, we can make 6x plus 6y equals 40. The bottom equation, we can make 18x minus 18y, and 3/5 of 40 is 24. Great, so we are now set with our equations. They look a little nicer than they started off, and this equation, these system of equations would be very convenient to use elimination by. So we're going to go ahead and multiply this first equation by 3 on both sides, and I'll write it down beneath. So now we have 18x plus 18y equals 120. Great. So if we go ahead and add these two equations together, we will get 36x equals 144. So we can divide both sides by 36, and we get that x is 4. So 4 being the rate of the canoe in still water, so 4 miles per hour is the canoe. So let's go ahead and find the rate of the current. So pick our equation. Let's go with our equation 6 times x, so 4 plus 6 times y equals 40. And so we have 24 here, so I'm going to subtract 24, and we get that 6y is equal to 16. And we'll go ahead and divide both sides by 6. And, ooh, scary. We got not a nice number, but that's okay sometimes. So we can reduce 16 over 6 to 8/3. If we wanted to put that as a decimal, that would be 2.6 repeating, would be the rate of the current. If you get a number like that and you're feeling a little uncertain about it, you can certainly go ahead and plug that number back in to the second equation to make sure it checks out. I can save you the suspense for this time and tell you it does. Let's go ahead and answer the question here by saying the rate of the canoe in still water is 4 miles per hour, and the current is 8/3 miles per hour. Awesome. Thank you again for joining us for this application of systems of equation. This is often referred to as current problems, where your speed in the air or in the water is being fought against the current or added to by the current, depending on which direction you are traveling.